I'll start by recording. So welcome back. This is actually the 6th week of class, and what we'll be doing today is finishing up our lecture on electric potential. So at the end of this lecture, we'll be done with all the content that's going to appear on the first test, which, by the way, is next Wednesday. Okay? I have the homework assignment that's due next week up here. It's actually going to be due on next Wednesday, because next Monday we don't even have class. That's the President's Day holiday. Actually, it's a holiday that comes in 2 days, Friday of this week and Monday of next week. So both of those days we'll have no class. Okay, so that means we'll only meet for lab this week, Monday and Wednesday. So Friday is not meeting for lab this week, all right? And then next week, obviously the Monday lab is not going to be meeting because we don't have class that day. And then Wednesday, we'll have the test and lecture, and then we'll have lab Wednesday and Friday of next week, okay? So that's all on the schedule on Canvas, if you forget. But just to remind you, those holidays are coming up and we won't have class. Any questions?
You said this Monday?
No, not this Monday, because we're here right now, but next Monday, we'll have no class. Also, this Friday, we'll have no class. So those are the President's Day holidays. Okay, so let's just launch right back into it. If you recall, where we left off was a discussion of how to calculate electric potential, that is V, given that we know the electric field E. So if we know E, we can calculate V. We were just going through a bunch of different examples of how to do that. So in this example, we had a charged conducting sphere. So here's what's going on. A conducting sphere of radius big R has a net charge Q, which is uniformly distributed over its surface. So that is to say, all of the charge is on the outer surface, none of it is on the interior of this conductor. What we're going to do is find an expression for the E field, and then we're going to integrate that E field to get an expression for the absolute potential as a function of distance from the center. So we can call that V as a function of R. And in order to do this, remember, we need to set the 0 point somewhere. We have to choose some point in space to say, at this point, V is going to be 0. And so just for the purposes of calculation, we're going to set that to be at infinity. Okay? So we'll set the 0 point at infinity, and then we'll figure out what this function V of R is. Make sense? So here, let's start with the first part of this. Does anyone remember, for a conductor, when there are no moving charges, what can I say about the E field inside of the conductor? It's equal to 0, right? So I can say that E is equal to 0 as long as R, small r, our distance from the center, is less than big R. That just means we're inside. And actually, the E field outside of this conductor is something we worked out in the Gauss's law lecture that we did actually 2 weeks ago now. So I'm just going to give you the result that we derived back then. As long as we're outside of the sphere, it basically just looks like a point charge E field. KQ divided by R squared, as long as we are at a greater distance than big R, which means we're outside of the sphere. So hopefully that looks familiar. We've seen this before. Okay? So here's what we're going to do next. I want you to consider a path that we can integrate over. Okay? Starting from outside of the sphere. And then going all the way to infinity. Okay, so let me just draw what that path looks like. Here is the conducting sphere, okay? We're going to start at some point outside of the sphere. And then we're going to take a path that goes outwards all the way to infinity. Okay? Now the reason I'm going to do this is because we actually know that the potential at infinity is supposed to be 0. So we want to bring that into our calculation somehow. That's why I'm going to end this path at infinity. Okay? So let me draw a vector along this path, which I'll call DL. That's just a little infinitesimal displacement along the path. So if you remember, delta V, that's the potential difference, is equal to minus integral E dot dl over this path. So that's what we're going to bring into play here. Now delta V, of course, is a final minus initial sort of thing. So my final potential is when I reach infinity, so I'll call that V infinity. And my initial potential, let's call this distance right here R. So this will be V of R. So just the potential when I'm some distance small r away from the center of the sphere. Make sense? That's the delta V side. Now on the other side I have minus, and then I'm going to integrate. Okay, what's my E field? Well, as long as I'm outside of the sphere, here's what it is. It's K, big Q divided by small r squared. And if I want to put a direction to this, it's in the r hat direction. It's pointing radially out away from the center of the sphere. So if I were to show the E field, it would be pointing outwards like this, okay? Now what about my DL vector? Well, since I'm basically just going radially out, I can call this dr, which is some infinitesimal distance we move, but then r hat just shows that we're moving in the radial direction, okay? So that's E dot dl for this situation. Does that make sense? Okay. Now V at infinity, what's going to go in there? 0. That's where we set the 0 point. Okay, so now I have minus V at R equals minus this whole integral. So basically I have two negative signs, might as well cancel them out, right? So I'll just say V at distance R is equal to, now remember, I have some constants, K and Q, which I can immediately pull out. And then R hat dot R hat is equal to 1. So that simplifies what's in the integral a little bit. And then all I'm really left with is dr divided by r squared, okay? Now I have to decide on how I want to express the limits of integration, okay? Now my top limit is going to be infinity, because that's the distance r that we end up at. My bottom limit, again, I don't want to put in a specific number here. I just want this to be sort of some generic distance we could be. So I'm just going to call that r, right? But of course, when it comes time to plug something in, you'll put in some number for r, okay? All right, so the question really is, like, how do I integrate this thing? It's just 1 over r squared. What does that integrate to? It's just negative 1 over r. So here I have k times q, negative 1 over r. That's going from r to infinity, okay? So the top limit is infinity, so I'll plug that in first. Also, I'll just pull this negative sign out real quick. I have minus kq, 1 over infinity, minus, plug in the bottom limit, 1 over r. And of course, this goes to 0. So what I'm left with is k, big Q over r. That's telling me, as long as I'm outside of the sphere that has charge on it, if I want to know the electric potential at some distance r from the center of that sphere, this is the formula that describes that, okay? All right, let's try this. What I want to do next is show you that if I'm at the surface of this charged sphere, so in other words, let's say I'm right there, right on the surface. Essentially what I'm going to be doing is plugging into this formula big R. Does that make sense? Because my distance is just the radius of that sphere. My distance from the center, if I'm right on the surface, is just the radius of the sphere. So I just want to establish what that is because we'll need to use this later, okay? So at the surface of the sphere, I'm going to plug in big R for my radius. And it's pretty simple what we get. K, Q divided by big R, okay? So to be clear, we haven't finished the problem yet. We've pretty much just done half of it because we've come up with a valid formula for the electric potential if we're outside of the sphere. But if we're inside of the sphere, that's a different story, okay? So let's think about that for a little bit, okay? So now, I want you to consider a different path that we could take and integrate over. So now consider a path going from little r equals big R, so that means we're at the surface of the sphere. And then we're going to take the path going inwards, so we're going to go inside into the interior. Interior of the sphere. Okay, so just to draw that real quick, it's like we're starting here, and then we're just following a path going into the sphere. So start here and here. Make sense? Okay, and what do? We say delta V for whatever path we choose is equal to minus E dot dl, okay? Integrated over the path. But over this whole path, I'm inside of the sphere, correct? And what do we know about the electric field inside of this sphere? It's zero, right? That means this whole integral is just zero, because E at every single point along the path is equal to zero. Remember, we're inside of a conductor, so that we know that's the case, right? But how do I express this delta V? Well, it's just a final minus initial sort of thing, right? So this is just V on the inside of the sphere, wherever we end up, minus V at the very surface of the sphere, which is this V of big R thing that we talked about earlier, okay? Well, that just means V inside the sphere is just the same as V at the surface, because the potential difference between the surface and any point on the inside is just zero. So that's K Q over big R. And it's important to note that this is a constant now, okay? Because little r is the distance that can change, but big R is just a constant, okay? It just tells you how big the sphere is. So what we have is, as long as we're outside, the potential appears to be decreasing with distance according to this formula, but when we're inside, it's just constant according to this formula, okay? So to sort of sum that all up, okay, here, let's take a look. We have KQ over big R, as long as we're inside the sphere, and KQ over little r, as long as we're outside, okay? And what that looks like, if we were to plot it out, just to be absolutely clear, we have constant potential inside the sphere. And then as soon as we go outside, it's falling off according to a 1 over r sort of relationship, okay? So do we have any questions on this particular example, how this works? All right, let me know. Let's keep it moving if there are no questions. So I want to stay with this result for just a little bit, just kind of see how we can apply it in a few instances. I want to talk to you about something called electrical breakdown, which you've undoubtedly seen before if you've seen a lightning storm, okay? That's just electrical breakdown happening on a very large scale. So when you have a very large amount of electric charge building up on some object, you also are building up very strong electric fields nearby, okay? So if you imagine, let's say the sphere in the previous example, right? The more charge we place on the surface of the sphere, the stronger the electric field right next to the sphere will be. And the thing is, you can't actually just dial up the strength of an electric field without limit. Okay, so something happens in the air in particular when electric fields get too strong, and that's called electrical breakdown. So in air, if the electric field exceeds this value, which is about 3 × 10⁶ newtons per coulomb, here's what starts to happen. So, as we know, right, if you have a charged particle inside of an electric field, that charged particle can be accelerated, right? The electric field is actually pushing the particle around. Well, in the air, you have a lot of free charges that are just present. In particular, you do have some free electrons just floating around in the air at any given time. And if the E field is about this value, those electrons are going to be accelerated so quickly that when they bump into other atoms, they'll knock electrons out of those atoms, creating more free electrons, and actually creating a conducting path for electric charge to flow through the air. And you may see this, of course, in lightning, in storm clouds. If a lot of electric charge builds up within those clouds, you'll get very strong electric fields building up in the vicinity, and this electrical breakdown of the air, which allows the charge in those clouds to flow to ground. But it can also happen on a smaller scale. You can just do this in a laboratory. You can just build up enough charge on an object and create this electrical breakdown. Okay, so for now, the important thing to remember is that if the E field gets about this strong, that's when electrical breakdown will happen in the air. If you're in a different material, by the way, besides air, there's a different value of E where this happens, but electrical breakdown is something that just generically happens in any material. Okay? If you turn up the E field high enough, you can make that material start to act like a conductor. Okay? So with that said, here's an animation of that kind of thing happening. And I want to do an example for you, okay? Now, unfortunately, I wasn't able to get my hands on one of these, but you may have seen a demo of a Van de Graaff generator before. Here's what a Van de Graaff generator is. It's actually a pretty simple device. You have a charged metal, you have a conducting metal sphere on the very top of the device. And then on the bottom, you just have this belt, okay? And basically what the belt is doing is it's charging this sphere by friction. So you basically just crank the belt, and as you do that, the conducting sphere is going to accumulate more and more charge, and eventually, if you put enough charge on that sphere, you'll cause electrical breakdown in the surrounding air. In other words, you'll create a little spark, something like this. So my question for you is, let's say we have a sphere with a radius of 25 centimeters. My question is, how much charge must accumulate on that sphere for electrical breakdown to occur? And then as a follow-up, what would the absolute potential, how many volts would the sphere reach in order for electrical breakdown to occur? So you're going to need two things here, of course. You're going to need to know the relevant formula for the E field, which we just went over in the last example, and the relevant formula for the absolute potential, which again, we just went over. So this is sort of a plug and chug thing. Try it out. I'll give you a few minutes, and then we'll go over it together. 3 times 10 to the 6 newtons per coulomb. All right, let's see if anyone has the first part. So for this first part, we remember that if I have a conducting sphere, the electric field is equal to 0 on the inside, and then it's given by kq divided by r squared on the outside. So we're interested in a point that's just barely outside of the sphere, so just right above the surface, okay? So at a point like that, we'd say the magnitude of the E field is k times q divided by big R squared, where big R is just the radius of our sphere, right? So what we want to know is q, it's going to be E big R squared over k, where for E, we put in what's called the dielectric strength of the air, or what is the value of the E field just before electrical breakdown starts to occur. As we just saw, that's 3 times 10 to the 6 newtons per coulomb, right? So 3, 10 to the 6 newtons per coulomb. The radius is 25 centimeters, or 0.25 meters. We'll square that. Okay. And then we'll divide by this. We have, anyone remember the value of K? 8.99 10 to the 9 newtons meters squared per coulomb squared. So if you take a look at the units, you can convince yourself that only coulombs will be left over. Newtons and meters will all cancel. And what do we get as a result of this?
2.09 times 10 to the negative.
Yeah, so I'm going to round that to 2.1 10 to the minus 5. And that's about 20 microcoulombs. Okay? So the sphere can really only hold 20 microcoulombs before it just discharges to the ground through the air. So you can't even put more charge than this on it.
That would make a really powerful battery.
Huh?
That would make a really powerful battery.
Potentially. So let's do the next step. V, right? At the very surface we just worked out is kq over r. And of course we'll plug in the radius of the sphere if we're interested in a point that's just above the surface of the sphere. So here we have k, once again, 8.99 10 to the 9 newtons meters squared per coulomb squared. Then we'll take our q value, 2.1 10 to the minus 5 coulombs, and then divide by the radius, 0.25 meters. Now, can someone tell me what that works out to?
7.5 to the 10 to the 5.
Yeah, 7.5 10 to the 5 volts. So almost 1 million volts is what we'd be charging this thing to before it breaks down. Okay? So that's just an example of how to use this result we just found. Okay, any questions so far? Keep going then. So I want to do a slightly different problem. It's going to involve integrating over an E field to get V as a function of R just like before. But we're changing the situation slightly. We're going to imagine that now we have a non-conducting sphere. So what changes basically is if we have a non-conducting sphere, the charge on it doesn't just have to be confined to the surface anymore. Instead, it can be distributed throughout the volume. So in this case, we're going to imagine we have a non-conducting sphere of radius big R. And it has a net charge Q uniformly distributed, again, not over the surface, but over its entire volume. So it's evenly filled out with charge on its interior. Find out an expression for the E field, and then integrate over that to find the absolute potential as a function of distance from the center of the sphere. So we're doing that once again. And like we did before, we're going to set the 0 point to be at infinity. Okay? Now actually, just to save a little bit of time, this is a problem that we worked out both in class during the Gauss's law lecture and in your homework. To find the E field due to a non-conducting sphere of charge like this. Okay? So you've seen that problem before. I'm just going to jump right to the result for what the E field is, and then we'll go from there, okay? So here's the E field. I'm going to just remind you of what we got when we did this in class, okay? So E, just kind of two expressions. Again, one is going to be valid for the inside of the sphere, and the other is going to be valid for the outside. So K, big Q, little r over big R to the third power is the one that's valid for the inside. So if we're on the inside of the sphere, this is what the E field looks like. It actually grows as we get further out from the center. And I'll put a little r hat unit vector next to that just to remind us that if we have a spherically symmetric distribution of charge like this, the E field is going to be pointing radially outwards. Okay? And then if we're outside, the E field just looks like before. Basically just follows Coulomb's law. That is, it follows the E field we'd expect for a point charge, but again, this only is valid if we're on the outside. So let me explain the process here, how we're going to work this out. We're going to start by integrating over a path that's just completely on the outside of the sphere. Okay? And we'll take the same path we did before. We're going to start from some point just outside the sphere and then go all the way to infinity. Then, after we've done that, we'll take a path that's only on the inside of the sphere. And that's how we'll get V as a function of R for any possible point in space that you want. Okay? All right, so here we go. Consider a path starting outside the sphere and then going all the way to infinity. Okay? So just to remind you what that looks like, here's our charged sphere. We're going to start some point outside, and then we're just going to integrate all the way to infinity. Okay? So there's our DL for this path. And then remember the E field is basically going to be pointing in the exact same direction, pointing radially outwards in this way. Okay. So remember, delta V is equal to minus the integral E dot dl. This is how we go from knowing the E field to knowing V. And just like before, delta V, you want to think of that as a final minus initial sort of thing, where V infinity is our final value of the potential, and then V of R is our initial value. So again, wherever we start, it's some distance, little r from the center of the sphere. Okay, then we have integral E dot dl. So let's do that. What do we have? We have K, Q divided by R squared in the R hat direction, dotted with dr times R hat. That's just, again, how we write a little bit of this displacement dl along the path. Okay? So a lot of this is going to look familiar, right? We've done this already. What's V of infinity? 0. That's where we set the 0 point. And then again, we have these two negative signs which will cancel. So VR equals, I have K and Q which I can pull out of the integral. And then I'm going to integrate dr over R squared between R and infinity. Okay? This is exactly what we did in the previous problem, right? So maybe we could just skip right to the answer because it's exactly the same. K, Q divided by R, okay? So this integral works out exactly the same as the one we just did. But remember, this is just if we are on the outside. This is a valid formula for the electric potential as long as we're on the outside of the sphere. Okay? Now, just like before, I just want to establish what the electric potential is right at the surface when the distance from the center of the sphere is big R. Let's KQ over big R, right? Just plug in big R right there. And we'll use that later. So again, so far what we've done is really no different from the previous problem. Because the E field outside of the sphere is exactly the same as in the previous problem, and we have the same 0 point. So we should expect this works out the same way. It's now when we go inside the sphere that things are different from before, because the E field is different from before inside the sphere. So the next thing I want you to think of is to consider a path starting from the inside So we're going to start from inside the sphere and then going to the surface. Okay, so let's imagine this. You're somewhere inside the sphere, it can really be anywhere, and then you take a path that you integrate over, which goes to the surface. Okay? Now the reason I'm choosing this kind of path, by the way, is because we know exactly what the electric potential is supposed to be at the surface. That's why I chose to put the endpoint at the surface. Just like before, I put the endpoint at infinity because we know exactly what the electric potential is supposed to be at infinity. Okay, that's the reason for making this choice. So, what we'll use is delta V equals minus E dot dl. It's the same integral as always that relates our E field to our electric potential. But now let's think about how this goes. Okay? Delta V. That's going to be V at big R. That's the electric potential at the surface. That's where I end up, remember? Minus V at small r. So I'm just going to assume my starting point has some small r distance from the center. Okay? And that's going to be E dot dl integrated between those 2 points. But now let's think about it. We have to choose the right E expression. We want to use the expression that's valid when we're inside the sphere. Okay, that's this one. So I'm going to write this one down. Okay, we have K times Q times small r divided by big R cubed. R hat, that's the E field inside of the sphere. We dot that with dl, which is dr times r hat. Okay? So now let's see what we can do with this. I'm going to make a few changes. V at big R, again, that's the potential at the surface. I'm going to replace that with this expression right here. KQ divided by big R. We know that's the case. And then minus V of little r. This is what we're ultimately trying to solve for right here. We want to know how potential depends on distance from the center when we're inside the sphere. So this is what we'll solve for eventually. But to do that, I have this integral that I have to think about, which is, okay, I have a negative sign overall. What are the constants that I can pull out of this integral, everybody? What would it be? K, Q, and then, yeah, the big R cubed. Remember, big R is just the size of this sphere. That's not changing, but little r, which is our distance from the center, that is changing. Okay, so now I just have r dr. That's my integral expression. And my limits, what would those be if I'm starting here and ending here?
0 to big R?
So I'm not necessarily going to say 0. I'm not necessarily starting right at the center. I'm just starting somewhere on the inside. So yeah, little r to big R, right? I start at some distance, little r, some generic distance, and then I end up at big R to tell me that I'm at the surface when I'm finished with this integral, okay? So yeah, the rest is just a little bit of calculus and algebra. It's not too bad, but we have to keep track of things, make sure not to make a sign error, all that. So let's go through it. So, first of all, what I'm ultimately trying to do here is solve for V as a function of R. So why don't I try to just put that on one side of the equation. So I'm going to take this negative term and put it over here, and I'm going to take this negative term, the integral, and put it over here. So what do I end up with? I end up with K Q divided by big R plus KQ divided by big R cubed times this integral, which is R dr. Okay, so just to rearrange to solve for what we want, that's what we have. Does that make sense? Now, we actually have to evaluate this integral. So if I just have R to the first power, what do I end up with upon integrating that? It's a half R squared, right? So first term is the same as before, constants out front are the same as before, but now I've evaluated the integral and I've obtained a half R squared, which we go between the two limits, little r to big R. Okay, so let's see what we have. We have K, Q divided by big R, K, Q. So here's what I'm going to do with this. I'm going to put the 2 that I get from integration, I'm just going to put it with the R cubed. So we have 2R cubed on the bottom, okay? And then when I plug in the top limit, I have big R squared minus little r squared when I plug in the bottom limit. Good with that? Okay, so notice how across the board, really I have kind of a common factor going on here, which is K times Q divided by big R. That appears in every single term. So what I'm going to try to do is just factor that out real quick. So if I factor that out, the first term is just this multiplied by 1, right? If we think about the second term, okay, that's K, big Q, times big R squared, but then divided by 2 big R cubed. So overall, if I combine these factors of big R, I'm just going to have big R on the bottom one time, right? And then the factor I'll pick up is a half. Okay, so this half factor comes from the second term right here. Okay? And then the last one, again, I have K Q divided by 2 big R cubed, and then minus little r squared. I can factor that all together. Common factor that appears in the parentheses is a half little r over big R squared. Okay, so this is just a nice way of factoring out this common term from all of these. Okay? Any questions on how that works? Okay. So overall, I have a 3 halves factor right here. Just combine the 1 plus a half, 3 halves. And then I have a 1 half factor over here. So I could write this, if I wanted to, as KQ divided by 2 times big R, 3 minus little r over big R squared. Okay? And, you know, I could keep trying to simplify this expression, but I think that's pretty good. Okay? Say it again? Yeah, I don't want to miss this, though. Do you see everything you want to see? I'm not sure what you wanted to see on this page. You good? Okay. So any questions on this one? We really did the same thing as before, except we have a different type of E field on the inside of the sphere. Yeah?
Yeah, I'm still trying to figure out. Like, I know how you got 1 over 2 the first time.
Right here?
The second time is like, no, the 1 over 2. No, a little bit down. Right there. I
Yeah.
kind of like got confused on that part.
All right, so this is just the third term, right?
Yeah.
There's a K, a Q, and then a 2 times big R, right? So because I have a 1 over 2 sort of thing, I'm pulling out the half right here. And then the KQ over big R is a factor out front. What do I have left over? I have big R squared on the bottom, because I need it to be cubed when I combine these two. And then I have a little r squared on the top. So I'm just sort of saying those two as a ratio squared. Okay? Anything else? All right, I'll leave this page at the front of the room if you want to see it, okay? But here's the takeaway. By doing this integration, we get two separate expressions for the absolute potential. One of them, again, is valid when we're on the inside of the sphere. That's this one, which we just went over. And then when we're on the outside, we have KQ over R, which is this expression, okay? So let me just show you what it looks like when we plot this out, okay? If I plot out this function, it's kind of slightly decreasing as we go out like this. So it reaches a peak right in the middle. But then, once we go outside of the sphere, so once we go outside of big R for our distance, we once again just follow a 1 over R relationship, just like before. Okay? So again, the specifics of this example are not really what's important, just you should know how to do this sort of process, to integrate over an E field to get V as a function of R. This is how it works. Any questions? All right, so we're going to keep it moving. So most of the last lecture and pretty much all of the first part of this lecture have been focused on how do we get electric potential, how do we get V from E? If we know the electric field, how do we calculate the electric potential? And as we saw, it's through integration, right? I have this idea that a delta V difference in electric potential between 2 points A and B is given by integrating the E field between those 2 points A and B, right? So this is what we've been talking about for a long time. We should have some sense from calculus that if we wanted to go the other way, that it would involve some type of derivative, right? In other words, if I go from E to V by integration, I should be able to go the other way by taking a derivative, okay? And that's exactly what happens. But we have to be a little bit careful about what type of derivative this really is, okay? Because remember, E, electric field, is a vector, right? So it's a type of derivative that we take that results in a vector for this to work out. So if you're in Calc 3, you may have seen this before. If you haven't seen this, don't worry, I'm going to explain it to you, okay? The way this works is E is given by minus, this thing is called the gradient of V, okay? It's like a multi-directional derivative. Has anyone seen this before in Calc 3, the gradient operator? Okay. So we're taking the gradient of V, and of course there's a negative sign out front as always, okay? Now what does this actually mean when we take the gradient? Well, when we take the gradient, let's say we're working in rectangular coordinates, x, y, z, okay? This is how it would work. I would look at my first term and see that it's minus the derivative of v with respect to x. And that would be accompanied by the I hat unit vector. So in other words, the x component of my E field is just the derivative of my potential with respect to x, okay? And then my next term is minus dv dy multiplied by the j hat unit vector. So that's telling me the y component of my electric field is the derivative of my potential with respect to y. And then the z component, same thing. Minus dv dz times k hat, that's telling me the z component of my electric field is the derivative of my potential with respect to z. Now, notice I'm writing the derivative symbol in kind of a different way. This is called a partial derivative, all right? Again, if you haven't seen this before, I'm going to go over it with you and show you some examples. Hopefully it's clear after the examples. But it's actually quite simple. If you're taking a partial derivative, that just means you're taking the derivative with respect to that variable alone. And you're going to treat any other variable as a constant. So in other words, if I take a look at this partial derivative with respect to x, I'm going to treat y and z as constants. If I'm taking this partial derivative with respect to y, I'm going to treat x and z as constants. As long as you know how to do that, you'll be fine. Just treat the other variables as constant. So to kind of generalize what this is saying, if I want to know what the electric field is in a particular direction, whether it be x, whether it be y, whether it be z, I take minus, because there's a relative negative sign out front, the partial derivative of the potential with respect to distance in that direction, whether it be x, y, or z. And just to round this off, the fact that there's a negative sign here is kind of important. It's telling us that the E field points in the direction of decreasing potential. So the E field lines are going to point in a direction where the potential is going down, not where the potential is going up. That's what that negative sign actually means. Okay. I want to show you one example of this. This is a familiar example. We found that the electric potential due to a point charge is given by V of R, which is equal to K, big Q, which is the charge, whatever that happens to be, divided by R. And in this formula, we assume the 0 point is at infinity. Okay, so what we just found is that if I want to know what the electric field is given this information, I should essentially be taking a derivative, okay? Now in this case, we're not dealing with x, y, and z coordinates. Instead, r, the radial coordinate, is what I'm using. So this says ER equals minus dV dr. In other words, if I want to find the electric field in the radial direction, I'm just taking the derivative with respect to my radial coordinate. That's dV dr. Again, there's a negative sign out front. Now this derivative is not too hard to do, right? I'm literally just plugging this function into here. And then we're taking a derivative. So, like always with derivatives or integrals, we can identify what constants we have, right? What are those constants in this case? K and Q. And those can just be pulled right out. So I have minus K times Q. And then I have a 1 over R sort of thing, but because when we take derivatives, we use the power rule, I'm just going to explicitly write this as a power. It's R to the minus 1 power, right? And what do I get when I take the derivative of R to the minus 1 power? Yeah, so the power, when we take derivatives, gets decreased, so by 1, so it's now R to the minus 2. And this negative 1 is a factor that comes out to the front. Okay, so let's see what happens. So I have minus KQ, and then now I've evaluated the derivative in brackets. And it's just like you said, minus R to the minus 2. That's the derivative of this guy. The two negative signs, we can cancel them out, right? And I can write this in a more familiar sort of way. If I have R to the minus 2, that's the same as 1 over R squared. So I can write this as KQ over R squared. And that's what we know the answer is supposed to be, right? We know that for a point charge, the electric field is given by KQ over R squared. That's Coulomb's law. But I'm just showing you, if you start here, you take a derivative, you recover Coulomb's law. So this idea works in this example, okay? Do you have any questions on how that works? Just taking a derivative to go from V to E. Let's do some more examples like this. This one I want you to try out. So suppose that the electric potential in some region of space is given by this weird function. It says V equals AX squared plus BXY squared plus C. A, B, and C are all constants, but X, Y, and Z, of course, are our coordinates, right, in that 3D space. So what I want you to do is find the electric field in each direction. That is EX, EY, and EZ. And remember that in order to do this, like if I want EX, I'm taking the derivative of this thing just with respect to X, treating everything else as constant, okay? So I want to do it with Y, take the derivative with respect to Y, treat everything as constant, and so on. So try it out, see what you get, and then we'll go through it together.
There's no Z.
Yeah, so there's no Z, and then get for EZ. It's 0, right? Yeah, so in this case, so a total derivative, you might have to apply like a chain rule at some point, but here we don't need to do that. We can just treat, you know, for doing dv dx, we treat y and z as if they're just constants for the purposes of the calculation. Yeah, looks like you got it. Okay. See if a few people are getting this. Let's go through it in case you don't have it. So I'm going to start by just copying down the function v. Okay, v equals ax squared plus bxy squared plus c. So remember, if I want ex, let's say I just want the x component of the electric field in this region of space. That's going to be minus dv dx. Okay? And that means I'm going to take this formula and plug it in here and calculate a derivative solely with respect to x. Again, that means y is treated as a constant and so is z. But actually z doesn't even appear in this formula, so don't even worry about that. Y is our constant here, okay? And of course, a, b, and c, we already know those are constants. So we just have to do this term by term, right? So my first term, ax squared. If I take the derivative of that, what do I get? 2ax. So here, I'll just put the negative sign out front, and then we'll do derivatives within this box. So 2ax, right? Okay, for the second one.
by2 over 2.
Yeah, so this is just like basically x to the first power with all of these other things in front of it as constants. So it's x to the first power, derivative just goes to 1, actually. And we just get by squared, right? Okay. So that's a formula for the E field in the x direction, right there. E field in the y direction, do the same thing, but my partial derivative is with respect to y. So I'm just going to put the same formula in a box, and now we'll do the partial derivative with respect to y. And again, we'll go term by term. So first term, ax squared. Yeah, so there is no y that appears there. So these are all just constants as far as y is concerned. So that's going to be 0. For my second one, it's just a y squared derivative where we have bx out front as constants, right?
So bxy.
Yeah, so 2y is the derivative here, and then multiply that by bx. So I have 2bxy. Make sense? And then I forgot to mention c, of course, but derivative of any constant, 0, right? So that's ey. Okay, ez. What do we think?
0.
Yeah, z actually doesn't explicitly appear here. So as far as z is concerned, these are all just a bunch of constants, and we're taking the derivative with respect to constants, we get 0. Okay? Does that make sense? So unless v is changing with respect to z, there's not going to be any z component of the E field. That's what this is telling us. All right? So hopefully you get the idea mathematically. Now, let's see another way of working this out. So let's say we have a region of space where instead of giving you some function for what the potential is, I'm literally just going to tell you at each point in space what the potential is. So in this case, it's very, very simple. It's 10 volts everywhere. So what can I say about the electric field in this region where it's just uniformly 10 volts everywhere? Give it some thought. What do we think? It's going to be 0 everywhere, right? Because what is the E field as we derive it from potential? It's given by a derivative with respect to our coordinates, right? So in other words, if I wanted to know the E field in the x direction, I would be taking the derivative of E as x changes. So in other words, I'd be looking for how my voltage is changing as I go along the x direction. But it's not changing at all, is it? As I go along the x direction? So surely we can say there's no x component for this E field, right? And then similarly, if I wanted to know the y component, I would be looking for, as I go along the y direction, how does my voltage change? Well, it doesn't change at all, okay? So there's no y component, and therefore there's just no E field at all. So if your potential is just uniform, it's the same everywhere, that automatically means the E field is equal to 0, okay? Because E field is associated with changes in potential as you move from one point to the next, okay? If it's not changing, you have no E field. All right, here's a slightly different one. So now it looks like the potential is changing as we move along in the x direction, but it's not really changing as we move along the y direction. So this time, I want you to calculate what the electric field is, and that means you're going to be able to tell me which way it's pointing and how strong the E field is. Okay, so try to work this out, see what you get. So we know that E is given by a derivative. See if you can use the information here to at least estimate what that derivative might be. So if you're stuck on this, let me try to get you started on this, all right? So I'll go back to that picture in a sec, but here, just if you're stuck, write this down. E is what we call the gradient of V. I should say it's negative, the gradient of V. There's a negative sign out front. And if we write this in x and y form, this is minus dV dx I hat, so that's your E field's x component, minus dV dy j hat. And since we're only working in 2 dimensions, we don't need to write a z component here, okay? So derivative of v with respect to x gives me the x component, derivative of v with respect to y gives me the y component. Now, which one of these can I just automatically say is 0? The y, right? Because we're not changing, v is not changing as y changes, right? That's how I know this derivative is 0. Now for the other one, just think of it this way, all right? We're not going to exactly calculate this derivative, but we can approximate it as delta v over delta x. So look on the graph between 2 neighboring points and see what the change in potential is, delta v. And then see what delta x is, see how far apart they are in the x direction. That's a good approximation of this derivative, okay? So try that out, see what you get. Make sense? So, going back here, give you another minute or so to actually compute that if you didn't do it already. It's actually, check your sign. Okay, so we're going to go through this, everybody, but here's what we're going to take from the graph, okay? I can literally just choose any two neighboring points, because as it turns out, in this case, we have a completely uniform E field. It's the same everywhere. So let's just say this. We'll go from this point, where my potential is at 40 volts, and then we'll just move to the right to this point, where we're at 30 volts. And notice that when we do that, I'm going from x equals 1 meter to x equals 2 meters, okay? So that's all the data we need to make the calculation right there. And we could have picked any other 2 points and it would have worked out the same way, okay? So here we go. What I have here is a negative sign out front, and then what's my delta V? Well, my final potential is 30 volts, my initial is 40, so I'm going to do 30 minus 40. What's my delta X? I end up at 2 meters. I started off at 1 meter, so it's 2 minus 1 on the bottom. So of course, we just have 1 meter on the bottom, and on the top, 30 minus 40 is negative 10, but becomes positive when we account for the overall negative sign out front. So this is positive 10 volts per meter, and I should have carried along the I hat unit vector through that, so 10 volts per meter in the positive X direction, okay? The E field is pointing in the positive X direction. Let's do something real quick, actually. You see that the units came out as volts per meter. That's not normally what we express E fields in, right? What's our standard E field unit? It's a Newton per Coulomb. So what I want to show you is a volt per meter is the exact same thing as a Newton per Coulomb. And sometimes you'll see it written as a volt per meter. They're totally interchangeable, okay? So let's just do a little work on the units. All right, units. Volts per meter. Okay. Do you remember how a volt breaks down into other units? A volt is the same as a joule per coulomb, if you recall. So it's an energy per unit charge. And then we're dividing out meters, okay? So just to write that in a more clear way, I have joules on top, coulombs, and meters both on the bottom, okay? Now, do you remember how a joule breaks down into other units? Well, there's a lot of ways to do it, actually. One of those ways is that a joule is a Newton times a meter. Remember, like work measured in joules would be a force times a distance, so that's one way to think about it. And then we still have coulombs and meters on the bottom. Meters cancel, so now we have newtons per coulomb. So these are the same unit, all right? From now on, you know that. So, any questions about how we did this? Hopefully it's pretty straightforward. So one thing I just want to emphasize, we found that the E field is pointing in the positive X direction in this case. Notice how, as we move in the positive X direction, our potential is decreasing. So our E field points in the direction of decreasing potential. It doesn't point in the direction where potential stays the same, okay? There's no E field in a direction where potential is just staying the same, okay? And that actually brings us to something called equipotential surfaces. If you're in the Monday lab, you already did this one last week, right? If you're in Wednesday or Friday, you're going to do a lab on equipotential surfaces next week, okay? But anyway, let's get into what this stuff means. So equipotential is kind of exactly what it sounds like. It just means equal potential. And more specifically, think of it as a group of points that all have the same potential. So if I can just find a bunch of different points in space that are all at the exact same value of electric potential, that's an equipotential surface when I take those all together. So in other words, if potential is the same everywhere, that means delta V is 0. There's no change in potential as I move along that kind of surface. So what we're going to get into is, what can we say about equipotential surfaces in general, but also how do we show them graphically? And so this is your first example of a diagram of equipotential surfaces. Typically in a diagram like this, what you're going to see is evenly spaced increments. So in other words, I could have each equipotential that I draw have a 1 volt difference. So maybe the first one I draw is at 1 volt, then the next one's at 2 volts, 3 volts. Or I could choose a larger increment. I can go from 100 volts to 200 volts to 300 volts. Whatever the case may be, we show it in evenly spaced increments, whatever the appropriate increment might be for a given situation. So why don't we take the example of a point charge? That's really the simplest case, so we can kind of go from there. Remember, for a point charge, electric potential, V as a function of R, is given by KQ over R. Okay? So let's think about it. How can we make all the potentials be the same? Or how can we make V be the same? Well, R has to basically be the same, right? So that means our equipotential surfaces are just surfaces where R, distance from this point charge, is a constant. So I'm just going to be drawing basically spheres, spherical shells around the point charge. And each one of these is going to be an equipotential surface. And if I also look at how this thing behaves, KQ over R, potential is decreasing, right, as R increases. So I have a very high potential to start off if I'm close, and it's just going to get smaller and smaller as I go out. So here I'm showing you 3 volts, 2 volts, and then 1 volt. That's what the equipotential surfaces would look like. That's shown in red. We also know what the E field looks like. That's shown with these black arrows. Okay? So hopefully that's pretty straightforward for how it would work with a point charge. Any questions on that? Okay. Now let's talk about some general features of equipotentials, okay? So as we said, this is really the definition of an equipotential. If you have an equipotential and you move along that equipotential, delta V is going to be 0 by definition, right? We also saw that E fields, they point from high values of potential to low values. We saw that in the example I gave you before, right? Where X, in the X direction, the value of potential was decreasing. The E field was pointing in that direction of decreasing potential. So E fields point from high to low values of electric potential. Another thing that we'll see is that E field lines are always perpendicular to equipotentials. All right, let's really try to think about why that's the case, okay? Remember how we calculated E from V? We took a derivative with respect to some coordinate, right? So if I have some coordinate where when I move along that coordinate direction, my potential is not changing, then I know for sure I don't have any E field along that direction. What I'm saying is, if I move in a certain direction where my potential is not changing, there's no E field along that direction. There's only an E field along a direction where my potential is changing in some way. So if this is my equipotential surface and I move along it, I know I have no E field in that direction. I only have an E field perpendicular to that direction, okay? And where does it point? It points from high values of the potential to low values. So it goes from high to low. Okay, the last point I want to make is that, let's say we have a conductor, okay, and that conductor is in electrostatic equilibrium. Remember, this is just a fancy way of saying there aren't any moving charges within the conductor, okay? In that case, the entire volume of the conductor will be an equipotential, okay? So, in other words, if you just move between any 2 points within the conductor whatsoever, your delta V is going to be 0, okay? So actually, for that last point, I just want to work that out for you real quick. So, again, I'll just draw some random conductor. And we're saying this conductor is in electrostatic equilibrium, no moving charges. Do you remember what we can say about the E field inside the conductor? Okay, so E equals 0 on the inside. Okay? So now I want you to imagine just any two random points on the inside of the conductor where we can start and end up, all right? I want to integrate the E field over over the path that connects those 2 points. So delta V equals minus the integral E dot dl, right? That's something we've seen about 1,000,000 times before. But in this case, if we're integrating between 2 points within a conductor, we know that the E field is just 0 the whole time we take that integral, right? So that just means delta V is going to be 0. So there's no change in potential as you move from one point within a conductor to any other point. Again, as long as there are no moving charges, this is going to be the case. So it's just the same value of V everywhere within the conductor. That's what this means. Does that make sense? All right. So those are some just basic facts about equipotentials that we want to know. It's going to help us solve problems, okay? So let's do an example. Let's consider this point charge Q, which is positive 4, 10 to the minus 9 coulombs. It's sitting right here. What we're going to do is find the radii. So like how far out from the center do we have to go to get to the equipotential surfaces where V is 10 volts, 20 volts, 30 volts. Okay? This is absolute potential with the 0 point at infinity. So we know the formula we're going to use here. Okay, so we'll find, again, the radii of these 3 equipotential surfaces. The next thing we'll do is we'll consider this scenario. Let's say we have an electron. We know the mass, we know the charge of an electron. It's given right here. And let's say that we place it at rest at this 10 volt equipotential line. So we start the electron off right here where the potential is 10 volts. What will the speed be when it moves to this 30 volt line? That's the question. And then the last thing is, how would this whole diagram change? What would look different about it if instead of a positive charge here, we just flip the sign around to make it a negative charge, okay? So there are a lot of questions here. Let's start with the first part, right? What are the radii for these equipotential surfaces? What are these radii here? Okay. So somebody tell me, what formula am I using when it comes to the absolute potential for a point charge? KQ divided by, yeah, just one factor of R. So essentially, I'm just flipping this around to say R equals KQ divided by V. Okay? So first, I'll calculate R, I'm going to call this R10. It's just the radius for the 10 volt equipotential line, which is found by taking K, 8.99, 10 to the 9 newtons meters squared per coulomb squared, times Q, which is 4, 10 to the minus 9 coulombs in this case. And then we're imagining this is our 10 volt equipotential. So we're dividing by 10. Can someone crunch those numbers real quick for me? Save you some time. 10 to the 9 cancels with 10 to the minus 9 here. So what do we get? Basically just 9 times 4 over 10.
3.6.
Yep. 3.6 meters. That's how far out the 10 volt equipotential line is from the point charge. Now, for the rest of these, so R20, that's basically just replace 10 volts here with 20 volts, right? That's going to tell us the radius for the 20 volt equipotential line. What would that be? Yeah, just work it out. You'll see it's 1.8 meters. And then R30, again, just replace 10 volts right there with 30 volts. What do you get? Yeah, 1.2. Okay? So we go back to the picture. So these are the calculations we made. This 10 volt line is 3.6 meters out from the point charge. This 20 volt line is 1.8. And this 30 volt line is 1.2 meters out from the point charge, okay? That's what we found. Now let's answer the second question about the electron, starting at the 10 volt line and then moving to the 30 volt line. Now first of all, let's just see if that makes basic sense, that it would move that way. We have a positive charge here, so of course, if we place an electron here, it's going to be pulled in and it's going to move closer to that positive charge, right? Because there's an attraction. And of course, as it moves in, it's going to be speeding up. So what we're going to do here is actually apply conservation of energy to solve this problem. Just the total kinetic and potential energy of this electron as it moves should be something that stays the same. All right? So that's what we'll use here. Does that make sense? Okay, so let's work it out. So this is the first question. For the second question, we have conservation of energy. That's what we're going to apply. So delta K plus delta U equals 0. That's the idea. Change in kinetic plus change in potential equals 0. And for delta K, here's how I'm going to write that out. It's going to be 1/2 mv final squared minus 1/2 mv initial squared. Which one of those two can I set to 0? Yeah, starts at rest, so that second term is 0. All right, this is a useful substitution that I showed you last time. But delta U, the change in potential energy of some charge as it moves through a potential difference, is given by Q delta V. So in other words, this potential difference delta V translates into a change in energy, delta U, if we simply just multiply by Q, okay? So that's what we're doing here. And that equals 0. All right, so V final, that's what we want to know. We want to know how fast it's moving at the end of this process. So V final squared, let's just do that first. So I have positive Q delta V right here. It's going to pick up the negative sign if I move it to the other side of the equation, right? And then if I multiply both sides by 2, I'll get rid of this 1/2 factor. And then if I divide through by m, I'll get rid of that m factor. And of course, we want V final, so we have to square root on both sides. Okay? Let's put in the values that we know. So we have under the radical, minus 2, and then Q represents the charge of our electron. So for that, we're going to have to put in a negative Q, that's minus 1.602, 10 to the minus 19 coulombs. Okay, delta V, that's our change in potential. Remember, we're going from the 10 volt line to the 30 volt line. So 30 minus 10 is our delta V. Now that's measured in volts, right? But remember, a volt is a joule per coulomb. So that is a useful way of looking at it because we see the coulombs will cancel. Now divide that by the mass of the electron, which is 9.11, 10 to the minus 31 kilograms. And someone crunch those numbers for me. And while we're doing that, let's just think about the units real quick, okay? Coulombs cancel out. And then I have joules per kilogram under the radical, correct? Unit-wise, that's what we have. Can anyone see a useful way of expressing the unit of joules here? Yeah, a joule is a kilogram meter squared per second squared. If you think about the formula of 1/2 mv squared, this should make sense, right? Because it's a mass times the speed squared to get an energy unit. Divide that by kilograms, take the square root. Okay, kilograms cancel, square root meter squared over second squared, meters per second. So it works out like you expect. Okay, just want to show you that.
2.65 times 10 to the negative 6, 10 to the negative 6.
So I agree with that, except it's 10 to the positive 6. Yeah. So that's the speed that the electron will reach going from the 10 to the 30 volt equipotential line. Okay? Any questions on how this works? Hopefully pretty straightforward. Okay, last question then. How would this all change if we had a negative charge instead of a positive charge? For that, just look at this formula right here for potential. So in our particular example, we happen to have a positive Q, right? If I make this a negative Q, I'm really just flipping all my potential values to the negative of what they previously were, right? So for example, let's look at the picture. If this were a negative charge with the same value, just opposite sign, this would be negative 10 volts right here, negative 20, negative 30 volts right there. That's how this would change. Does that make sense?
Listen, I want to have a question.
Okay. From
Feedback after the speed.
here.
Yeah. Now let's say you have a positive charge.
Okay. So if you had a positive charge, this just wouldn't work because it would not move inwards, right? If you had a positive charge,
A negative charge, like you said.
yeah. So I'm saying, but are you asking if we had a positive charge here?
Positive charge, yeah.
Yeah, so basically there would be no solution to this because it wouldn't want to move in that direction, period. It would want to move in the opposite direction. It would want to move outwards, right? If you had a positive charge, it would be repelled from that central charge. So it would have no reason to accelerate inwards. It would actually accelerate outwards.
In that case, you can't have the speed, right?
Yeah, because it doesn't move that way. Yeah, so there's no solution to this. That's correct. Okay, you see what he's saying? If I have an electron starting here, of course it's moving inwards, right? If I have some kind of positive charge starting here, it doesn't move inwards at all. It actually is going to move outwards. Okay. Now for these, I'm just going to show you some examples. Okay. And in these examples, I want you to just see some of those features of the equipotential lines that we talked about before. Namely, that the E field points from high to low potential, and the E field is perpendicular to the equipotential lines. Okay? It takes a lot of computation to see where this sort of diagram comes from, so I just want to show you the diagram and explain some of the features on it. Okay? So here's the first example. We have two charged plates. We have a positive plate and we have a negative plate. Now actually, we kind of have a sense of what the E field looks like already, right? It's basically pointing from the positive plate to the negative plate, and it's more or less uniform on the inside, okay? So as we said, the equipotentials are going to be perpendicular to the E field. So I'm showing you the E field here in black as a solid line. The equipotentials would be right here, going perpendicular to the E field at all points. Okay? And again, we're going from high potential to low potential. That's the direction the E field points in. Okay? Remember the electric dipole? This is a case that we've seen in the past, right? Where we have a positive charge and a negative charge separated out by some distance. And we know what the field looks like, right? The lines are going to be coming off the positive charge and then eventually terminating on the negative charge, right? So those are the E field lines. So if we want to know what the equipotentials look like in this kind of corresponding diagram, they're going to be not perfectly circular, kind of elongated circles that are surrounding each one of these charges. That's how you can make them perpendicular to the E field at every single point, okay? So again, with black lines, we're showing the E field. With these red dashed lines, we're showing the equipotentials. Okay, and if you do the equipotentials lab, you're going to do an example just like this and an example just like this and map it all out on a piece of paper. All right. Here's another example. Again, I want to make sure this is getting across. So here's an equipotential map. Okay. What you see here is basically an oval labeled 0 volts. What does that mean? At every single point along this line, we're at 0 volts. This one's labeled 1 volt, meaning at every single point along that line, we're at 1 volt and so on, right? So we're going to go 0, 1, 2, 3 volts. These are the 4 equipotentials that I'm showing you. So we're going to do a few different things. First, let's estimate how strong the E field is here at point A. Okay? And then the question is, what is the direction of the E field there at point A? Then what we're going to do is rank the strength of the E field with points A, B, and C. So where is it the strongest? Where is it the weakest for points A, B, and C? And then we're going to make a sketch of the electric field lines. Because if we know the equipotential lines like this, we should know enough to say what the E field looks like in a rough sense, right? And then the last question is, what is the sign of the charge within this equipotential line? We know there's some kind of charge in here. That should become clear once we draw the E field, actually. And we just want to know, is there like a positive charge or a negative charge here that's creating this map in the first place? Okay? So, a lot of questions there, but let's go through it. Okay, for the first question, we're estimating the strength of the E field here at point A, all right? So when we do this, let's use a coordinate system where, let's say the positive x direction is to the right, going this way, and the negative x direction is to the left. Let's say the positive y direction is going up like this, okay? So just to keep track of coordinates, let's use that. At point A, what can I say about the E field? Is it going to be in the x direction, the y direction, or some combination of both? Yeah, it's only going to be in the x direction because potential is not changing as we move in the y direction here, okay? Like imagine, again, I'm right at this point. If I move up or down, I'm still at the same value of potential more or less, okay? Potential is only changing as I move this way. Okay, so that's an important thing just to see from the diagram. So let's work it out. So we could say EY is basically equal to 0. And then for EX, we know that's minus dV dx. But I can approximate that in the following way. I'll just write that as minus delta V over delta X. So we're not going to take a proper derivative where, the dx is, taken to be the limit where that approaches 0. We're just going to actually do it this way, approximate it with some kind of finite change in V divided by some kind of finite change in X. So going back to the diagram, as I move in the positive x direction from here to here, what's my delta V?
1.
Yeah, it's positive 1 volt. I increase by 1 volt, right? And what's my delta x? That's 1 centimeter. Just give it in the diagram. So just 1 volt divided by 1 centimeter, correct? So my delta V is 1 volt. My delta x is 1 centimeter, or 0.01 meters. But remember, we have this negative sign out front at the outset. Okay? So that's about minus 100 newtons per coulomb. Okay? So that just means the E field is pointing in the negative x direction, which we're assuming is to the left here. Okay? So at point A, we have an E field, which is 100 newtons per coulomb, pointing to the left. Okay? The next question has to do with ranking the E field strength between the 3 points shown. And for that, again, I'm just going to remind you that EX equals minus delta V over delta X. But if I just want the strength of the E field, don't worry about the negative sign, okay? So here's the thing. Remember, my equipotential lines in the diagram are evenly spaced. So if I go between any two of those lines, it's just a difference of 1 volt, right? So if I'm just taking one line to the next, it's always 1 volt, right? Delta V on top is the same. But the distance between two neighboring lines can change, right? Some of the times in the diagram they're really far apart, other times they're really close, right? So if delta V is the same for all of these different cases we're going to look at, the strength of the E field is like inversely proportional to the distance between the equipotential lines. You see that? That just means the closer together the lines are, the stronger the E field is. And the more spaced out they are, the weaker the E field is. Okay? So strongest where equipotential line spacing is smallest. Okay, does that make sense? So go to the diagram and we'll see where that's happening. So where do I have the strongest E field based on that reasoning? Point C, right? Because I make a jump of 1 volt over a really tiny distance at point C, right? Where is it the next strongest? B. So I make that same jump of 1 volt from this line to this line over, a slightly smaller, a slightly larger distance than before, right? And then the weakest E field is point A, because I make that 1 volt jump over the biggest distance there. Does that make sense? So the ranking would be strongest at point C, then B, then A. So just CBA, right? So let's actually just write that down. The E field strength at point C, bigger than the E field strength at point B, bigger than the E field strength at point A. That's the ranking we would attribute to this, okay? All right, does that make sense, everybody? All right, so I'm going to flip back and forth between this and the picture, so hopefully you have this down. Let's go back to the picture. Sketch the electric field lines. Okay, how do we do this? What's the general rule that we follow?
Perpendicular.
They have to be perpendicular to the equipotentials, right? That's what we know about the E field. And what direction do they point in? They're going to go from low to high potential. That's how this works. So let's think about it. Let's just say we want to start at this point and then just sort of map out which way the E field's going, right? So if I'm starting here, my E field should be going in, right? It should be going in the direction of decreasing potential, but it should be staying perpendicular to these lines. So basically at this point, just going straight in like this, right? All right, what if I'm over here? Let's think about that. I'd be going from 3 volts to 2 volts to 1 volt to 0 volts. So now this is the direction of decreasing potential if I'm on this side. You see that? So basically, in a rough sense, the E field lines are just going inwards. Because they have to go from high to low potential, but they're not just going to be perfectly straight lines, because they have to curve to keep it at a right angle to the equipotentials at every single point. So notice how every single point where my E field intersects the equipotential, it's at a right angle. Okay? And just using those two facts, again, it's perpendicular to equipotentials, goes from high to low, allows us to come up with this picture. Does that make sense? And that allows us to answer the last question. You see how I have some E field lines just going in towards this region? What kind of charge do I have in that region? I must have some negative charge there for the E field lines to be coming in towards that region. There's a negative charge there. Okay? Any questions? Does this make sense? So again, computation-wise, this stuff is not too bad, but got to get this concept down. Okay, here's a question for you. We have equipotential lines at 1 volt, 2 volts, 3 volts, 4 volts, like this, shown in red. And then I have 3 points, A, B, C, D. I want you to figure out how to rank those points in terms of the strength of the E field. So where is it strongest, where is it the weakest? So let's just do that real quick. Where is the E field going to be the strongest? Yeah, so remember, the idea here is it's wherever the equipotential lines are most clustered together is where you'll have the strongest E field. So it looks like point C is where the E field would be the strongest. Would we agree? Okay, what's next? So I would say, based on this diagram, A and B should have roughly equal strengths in terms of their E fields, but it's certainly going to be less than here at point C. And then where's the E field going to be the weakest? Yeah, so pretty much the ranking goes as shown in the picture. Strongest here, probably equally strong between these two, and then the weakest over here. Does that make sense? And you can just determine that based on the spacing of those lines. Okay, question then. Which way is the E field going, roughly speaking?
Left.
Yeah, well, yeah, it's gonna kind of go inwards. And if we're talking about along this line, it's going to the left, right? Because it's going in the direction of decreasing potential. It would go from the 4-volt line, point towards the 1-volt line, right? So just imagine we have an E field pointing that way, to the left. Okay, so based on that, if I take an electron and I put it right here at point A, and it starts off at rest, which way is it going to move? Is it going to move up towards point B, towards point C, or point D? Let's put it to a vote. Okay, I think I heard a few different answers, right? So who thinks the electron, if I put it here at point A, is going to move towards point C? Who thinks it's going to move towards point B? Who thinks it's going to move towards point D? Okay, basically all of us. Good. Remember, E field's going this way. Electrons, which are negatively charged, they feel a force going against the E field. So that would move it over here, right? What if it was a proton?
It would go toward the center.
Yeah, a proton would be a positive charge, so it would be feeling a force going exactly with the E field lines. That would move it towards point C. Does that make sense? So this is the kind of information you can take away from a diagram like this. Hopefully you're starting to see some of the features here. All right, here's an example for you. This is what we'll end on. So we have two electrically charged conducting spheres. The radii of these two spheres are R1 and R2. Okay, so we just have two conducting spheres, radius R1 and radius R2. And initially, they both have some kind of electrical charge on them. We don't really even need to say what the electrical charge on each one is to start, just there's some kind of charge on each one starting off, okay? Then, we connect the two spheres with a metal wire. So, basically, we're allowing charge to move from one sphere to the other. There's now a path for charge to move from one sphere to the other. That's what's happening. Okay. So the spheres are both conductors. The connection between them is a conductor. It's basically just one big conductor when we connect them in this way. Does that make sense? You can essentially now think of this whole thing as one big conductor. What did we say about electric potential in a conductor?
It's evenly distributed throughout.
Well, in an electrical conductor, potential is the same everywhere. So as soon as we connect them like this, we basically are ensuring that the electric potential is the same everywhere between these two conductors. Does that make sense? Okay, so the two spheres, once connected, we can consider them to be acting as just a single conductor, so they now have the same potential. In other words, V1 equals V2. Same potential for the two spheres. But now what I'm going to do is bring in a formula which we derived earlier in the lecture for what is the electrical potential at the very surface of a charged conducting sphere like this. Well, it's just KQ over R, if you recall. So for each one of these, I'm going to just replace KQ over R with V. So for the first one, that's KQ1, whatever charge ends up on that one at the end of the process, divided by R1, the radius, equals KQ2 divided by R2. So that will be what we can set equal once we've connected the two spheres. But here's what I'll do next. We know that we're dealing with conductors, so we know that for a conductor, all of the charge is going to have to reside on the surface. So it makes sense to think about surface charge density, sigma, in this situation, okay? I just want to remind you, sigma, when you see this variable, it means charge per unit area. It means Q divided by A, basically. So to rearrange that, you can just say Q is equal to sigma times A. The charge on each one of these spheres is just the density on the surface times the area. Okay, does that make sense? Just bring it in the definition here. Since we're dealing with a sphere, what can I say about area? What is the relevant formula for area? Yeah, the surface area of a sphere is 4 pi r squared. So I'm going to put that in there for area. So for each one of these, if I want to express what the charge is, I can write that as sigma times 4 pi r squared. I can do that for Q1. I can do that for Q2. I can make that substitution. Okay? Here's what it looks like when I do it for Q1. I have K, that's always there. Sigma 1, 4 pi r1 squared. Again, that's just my substitution for Q right there. Divide R. Then, same thing for 2, right? It's the same exact expression, but with 2 subscripts. Okay, how can I make this simpler? Well, I have a K factor and a 4 pi factor, which I can just get rid of across the board, right? And then if we look over here, I have an R1 squared divided by R1. That's just R1 overall. And I just have an overall factor of R2 here, okay? So what does that tell me? Sigma R1 equals, sigma 1 times R1 equals sigma 2 times R2, okay? So now this may seem like sort of a strange niche problem, but the last thing we'll end on in the last couple of minutes we have is how does this actually practically apply, okay? So let me talk about that next. So first, just notice sigma times R is just a constant. You can think of it that way. If we have just a giant conductor like this, connected spheres, sigma times R is just a constant for that conductor. So think of it that way instead of just it's equal between 1 and 2. This quantity here is a constant, okay? So if we have some kind of charged conductor in electrostatic equilibrium, again, that just means charges are not moving around, they're staying still. This quantity, sigma times R, remains a constant. And let's try to think about what that means, okay? So as an example, take this crazy shaped conductor right here. Imagine there's some kind of charge on it. Let's just say it's net positive charge, for example, okay? What we're saying is sigma times R is constant for this conductor. Okay, well, R, think of that as the radius of curvature. Okay, it doesn't necessarily have to be a spherical shape we're talking about here. It's just a general radius of curvature. So for example, if I'm looking at this point right here, it's nearly a straight line, isn't it? And the radius of curvature therefore would be very, very big at this point, right? Whereas where there's a very tight curve right here, the radius of curvature would be comparably smaller. This is saying that when the radius of curvature is smaller, when R is smaller, sigma has to be bigger, right? Because the product of the two has to stay the same for the conductor. So that means where the radius of curvature is smaller, the density of charge is greater. In other words, there's more charge piling up in these places. And that's what I'm trying to show you in this diagram. Charge is very sparse, where we have a small radius of curvature, and it's very concentrated where we have a large, sorry, I said that backwards. Charge is very sparse where we have a very large radius of curvature here, and it's very clustered where we have a small radius of curvature over here. And that's just what this equation is telling us is going to happen. Okay, so if you have a conductor with some charge on it, they have very sharp edges and points where R would be very small. Sigma is going to be very large. You're going to have a lot of charge piling up at those points. Okay? And as we know, if there's a lot of charge piling up, there's going to be a very strong electric field in the vicinity of those points, right? that might be something you're trying to avoid in a given situation, right? Because maybe you can cause electrical breakdown if enough charge piles up. And of course, if we're talking about, let's say, a transmission line or something like that, that's definitely something you'd want to avoid. So there are ways of preventing that from happening. For example, if you've seen these sorts of corona rings on a high voltage lines, that's what these are for, is to prevent electrical breakdown in situations like this. So that's all the time we have today. On Wednesday, we're actually going to start a new chapter that is not covered on the test, but we just have to get ahead in the material given the holidays that are coming up, okay? So see you on Wednesday. And we do have lab this week, Monday and Wednesday, so today and Wednesday, but not on Friday.